Okay, good morning, everyone. Hola, hola. Good morning, everyone. So it's a pleasure to me to present Carlos Quintero, who 99% in this room know very well. But anyway, I cannot do it in Japanese so far. Next time I will do. So Carlos is a great colleague of everybody here, and he is in-house researcher. He made all his career here. He studied at the University of La Laguna, then he did his PhD thesis here, starting with Valentin and continuing with David Orozco and in Basilio. And then he moved to Japan to work for JAXA for 4 years, where he also did a great career and progressed a lot in analyzing observations from Noda and other satellites in the Japanese community. And after that, he was also for a year in Oslo. And since then, in 2020, he moved here back to the IAC, and he's now a postdoctoral researcher in the solar group. And today he will present his recent results about solar physics.
Hello, can you hear me? Thank you very much, Lena, for the introduction. Today, as you see, the title is a bit long. The important thing is that the organizers of the meeting asked me to present more or less about my career and also the Ramón y Cajal project that I would like to develop here, because as you probably know, I was awarded a Ramón y Cajal last year, and I started this year as a Ramón y Cajal. So that the problem is that for me it was a bit difficult to decide how I can approach this challenge of introducing myself and making it in a way that a broader audience can understand it. So what I did was, okay, let's divide just more or less in two main topics, what I usually do. As you can see, I put them in 2 points. So the analysis of high spatial and spectral resolution polarimetric observations of the sun with inversion codes, and supporting the development of future instruments through theoretical studies. As you can see there are many words that probably require some explanation, and actually this is what I am going to do. So I divided them with colors, and I would like to start this presentation covering what I mean by these different topics, and then try to link them to what I usually do. So then the goal is to get an idea of what I'm doing. So I'm not going to enter in many detail in any of them, but I hope you still will get an idea of what I'm doing. And at the same time, I will be able to show you what I'm doing with all my career and from now on. So then let's start with the first one. And from the first one, let's start with the blue color. So high spatial resolution, so high spatial and spectral resolution observations. So what I mean by that is that we can observe the sun in different ways. So here you have an image of the full disk observed from space. And you can see that is a very beautiful image where we can see that the sun has a rounded shape. And also you see that you have different features inside the disk. But the idea is that when we refer as a high spatial resolution observations, what we mean by that is pixel size that is really, really tiny. It's around 100 to 100 kilometers per second. So then in general, we are not able to observe the full sun with such high spatial resolution. So what we usually do is to try to follow similar approach as we will do with a microscope. So we are going to cover just a small part of the sun, but we are going to cover it in high detail. So we are aiming to see the tiniest elements that we can see in the disk. So then in that sense, what I have been using during my career are space observations, particularly the Noda spacecraft. And then here you can see that now the field of view is much, much smaller, but we are seeing the structures that we just had a glimpse before. We are seeing them in great detail. So we are seeing black parts, then small bright points, and then even inside the, this is going to be challenging. These tiny things that we have here that of course they were not visible before. So then the idea is that we have less field of view, but we can get in a greater detail. And also I mentioned spectra resolution. So then in this case, we have the same field of view, but what we are plotting in the top part is the continuum. And so the spatial distribution of intensity at the continuum. And then in the lower part is a different wavelength, a line core of a reference spectral line. And you can see that selecting different spectral regions, we can see that there are also different intensity patterns. Okay, and then I also use balloon-borne telescopes. And in this case, what we have is that they are a middle ground between ground-based telescopes and satellite telescopes, in the sense that they fly very high. They are stratospheric balloons, so they are around 30, 40 kilometers. So then they are at a height where the atmosphere, the Earth atmosphere is almost absent. So then they have similar conditions to a spacecraft. But at the same time, the lifetime is just maybe 2 weeks, 3 weeks. So then it's a mission that is much, much cheaper than a space mission. So then we have similar conditions, but they are much easier to build and to develop. And at the same time, they have also very high quality. So here we have, again, just a reference that we are not seeing the full disk of the sun. We are just seeing small parts, but with very, very, very high detail. And then finally, I also use ground-based telescopes, in particular, the Gregor telescope that is installed at the Observatory del Teide. And in this case, one of the observing modes the instrument have is that it's an even tinier field of view. It's just the dark box that you see here. So we are much, much, much a smaller field of view than before. But this is an integral field unit, so it allows us to study not only the spectral information, but also the spatial domain, the 2D spatial domain at the same time. And here, for example, we are just seeing that when we perform a small mosaic of 3x2, we can get the evolution of different events. In this case, we have just something with high energy appears, and then it disappears. And the idea is that this is something that we basically can only do with an integral field unit. And even if you believe that they look like a step back because the field of view is so small, but the idea of having the three-dimensional information strictly simultaneously is actually what I believe is the future of astronomy. The only thing is that currently sensor technologies are slowly getting there. So then the main limitation for the field of view essentially is the pixel count that we have. So if we can get much, much bigger sensors, then we can also increase the field of view. And just as a note of something that I really like to present here and to say it, you will see that I will say it later on as well, is that this integral field unit, it was the first one that was developed, tested, and offered to the community in the world. So I just want to say it now, and I will say it also later. The solar physics that we do here is one of the top class. And even as I said before, it may look like we are going back respect to the previous observations. This is actually a step forward. Okay, so now next color, polarimetric observations. So then in this case, what we have is that we use a polarization modulation unit. And then what we do is that we don't only measure fixed spectral wavelength, we measure the spectral information of specific spectral lines, but also we measure the polarization degree. So then in that case, we observe usually the four Stokes parameters. So then we have that rows here are different spatial pixels, but this is just the same spectral domain. So then we have that we observe usually intensity, and then linear polarization, and then circular polarization. And you can see that selecting different pixels in a reference field of view, the signals are different. And the importance of doing that is that if we are able to get the polarization degree of the solar light from there, we can infer the information of the magnetic field vector. But this is also very important for us if we aim to understand the physical phenomenon of the sun. So then, from the previous observation that I showed you, remember that I said continuum intensity on the top and then line core intensity on the bottom. We can expand this information now, including the linear polarization degree and the circular polarization degree. And as you can see, they look very different. And this is because they are providing information. No, not very different, but they provide an additional information. And just as a reference, we are pointing close to this center. So essentially, this linear polarization degree is giving us information of the magnetic field component parallel to the solar surface. And then this circular polarization map is giving us information of the longitudinal component of the magnetic field. And colors indicate just sign. So then, as you can see, just measuring the polarization degree and also the spectral information, so we are getting access to the thermal, the dynamics, and also the information of the magnetic field vector. So then, the next color is inversion codes. What we would mean by inversion is that they are codes that aim to start from the polarization information that we have, and they want to go back. So in the sense, the name of inversion, and then they want to go back and infer the physical parameters in the sun when we observe this polarization, the information. So then the idea is that we start from a spectral information, and we aim to have the physical information of temperature, velocity, or magnetic field. So then how we do that? So then the codes are able to solve the transfer equation with different approximations, but the idea is that the codes will generate a synthetic profile. And then the idea is that they will start with a gas atmosphere, they will generate a synthetic profile, and then they will compare it with the observed profile. If the profiles are similar, then we can assume that more or less we are getting the atmosphere that actually was in the sun when we performed the observation. If the synthetic profile is really different, then it means that our gas atmosphere is off, and we have to change it until we get a good fit. And this is usually done with least square methods. Just as a reference, this is just more or less the main core of the minimization method. And the idea is that we are going to compare in each iteration the observed profiles. So in this case, K will go from 1 to 4, so it's I, Q, U, and B. And also we are going to do the comparison in wavelength. So it's this I here. So then we want to have a good fit in wavelength and for the first Stokes parameters. And again, every time that you will see this tick here, is again a remark that this was a development that was done here at IAC for the first time. And actually this one represented also the baseline for most of the modern codes that we have these days. So again, emphasizing that solar physics that we do here at IAC is really top class. So then what do we do with inversion code? So this is the example from before. And if I just move ahead, you will see a reference fit. Maybe it's there's blue lines here. Maybe it's easier, better when the fit is not so good. But just again, so we start from the black, we apply the inversion code, and we get some fitting accuracy. So then in general, fits are good, but the problem in some cases is that we may not have enough signal. So then in some cases we are dominated by noise. So then there are some challenges to fit those profiles, because actually if you have noise, the solution is not really accurate and you have a lot of uncertainties. But if we focus on the cases where we have signals and we get a reasonable fit, then we can assume that actually we can study the atmosphere that we are getting from the inversion process. So then we move ahead. And then, for example, There are some cases where inversion codes, they just give you a constant value, but the codes that I usually use, they will give you the height stratification of the atmospheric parameters. So then we can do, for example, a type of plot like this one. So that in this case, what I have inferred from the observation is the temperature, that is the first row, the line of sight velocity, second row, the magnetic field strength, third row, and the magnetic field inclination, fourth row. And as I said, I'm also inferring this with different heights. So then we can study not only the spatial distribution of the physical parameters, but we also can study how they evolve with height. And then in this case, is the sunspot that I presented at the beginning from the balloon observation. I'm just focusing on a small part where we had some activity. And then the inversions reveal that the temperature has some structure here, but then we have a strong enhancement here that, as I will briefly discuss later, it coincides with a high energetic phenomena that happens in the sun. And then you can see that also, for example, if you study velocities, you have that red, it's downflows, and you have that some areas inside this structure, they show downflow velocities in lower layers, and then they become a different sign in upper layers. And the same happens with the inclination. So then what we are getting from here, more or less in a broad term, so we have energy release, we have opposite directed flows, opposite directed fields. So then here we are getting from the observations that probably we have some kind of magnetic connection here that is actually producing this release of energy that we are seeing. So I cover the first part, and now let's move to the second part. And again, I divided in colors the main topics so we can go slowly and cover them in detail. So as Elena said, after my PhD here, I moved to Japan, to JAXA. And there I started not only to analyze, the data and to analyze data from different observatories, but I also wanted to do some instrumental development. And here you can see me behind our group at that time. And the idea was that as I was able to use inversion codes and also to do forward modeling, so they asked me if I could try to somehow reproduce the capabilities of different instruments that they were developing to understand how capable they were of performing a specific scientific goals, or in other case, to try to optimize them. So then the theoretical studies aim always to reproduce as much as close as possible the observations to try to the instrument, theoretical instrument, in order to be able to estimate if we really were going to succeed in our scientific goals. And then those theoretical studies, they are in the opposite direction as the normal inversions. So now we have that we will start from a realistic MHD simulation, could be 2D or 3D. So then in this case, we know beforehand all the atmospheric parameters, temperature, line of sight velocity, longitudinal magnetic field. And then the aim is to use this as an input, then solve the erratic transfer equation, generate synthetic profiles, reproduce the instrument conditions, and then try to see if with different approaches we are getting close to the atmosphere that we have in the simulation. So then in that sense, for example, just let me show you an example and then I will go in detail. So in this case, it was one of the first studies in 2016. We have that in the top part, there are different cuts of the temperature. So they have a spatial domain, and then the different columns from the left to the right at different heights. And then in the lower part, they are specific spectral wavelengths of one of the candidate spectral lines that they have for one instrument. So then I did the synthesis, and then one of the first things that we could do is that if we select different spectral parts of the spectral line, can we see some relation to the temperature from the original simulation? And you can see that in general, they look very close, not every time, not everywhere, but just with this simple study, we started to get a hint that this spectral line for analyzing, for example, the temperature at different heights was very capable. So then the goal of these studies was always, if we have this selection of lines, are we going to achieve our scientific goals or not? And then the idea is that I use many spectral lines, and also I use for the time where we have more or less a selection of the spectral lines, then we use different physical scenarios. So in some cases, we have more magnetic field. In some cases, we have flows. In some cases, we have twisted magnetic fields. So in all cases, we always wanted to check or to verify that we, at least theoretically, we were going to be able to have access to this physical phenomena with the instrument configuration that we were designing. So then after that, after returning to the IAC, I wanted to continue in this direction, but actually I wanted to also get a bit more involved on the, let's say, instrument side and also management side of the developing of a mission or infrastructure. And then I work a lot on the European Solar Telescope. Here is just a concept that we published in the 2022 paper. And again, there's a tick there because the European Solar Telescope is going to be the forefront of the solar observations in Europe and probably the world. It's a really, really ambitious mission. It's going to be very big. It's going to be very capable. So again, the IAC is leading or co-leading another future development that's going to be state of the art. And then in the case of Greece, it's already an instrument that has been working for several years. So in this case, was also more related to upgrading the instrument. I mentioned before the integral field unit. The instrument has been also receiving different upgrades related to performing multi-channel observations and different things that we have optimized and updated in the last years. And also more recently, I've been also working with similar studies, theoretical studies, and also helping a bit with the design and the management on another instrument. The name is very big, but the acronym is EMBER, so it's easy to remember. And again, this case is an instrument for EST. It's heritage somehow of Greece, but it's much, much more ambitious. It's going to be, again, an integral field unit based instrument, but it's much more ambitious in the sense that it wants to have higher spatial resolution than Greece, but also much higher field of view. So then this put a lot of constraints on sensor and also the integral field unit design and size. So again, I put a tick here just to emphasize that hopefully the IAC will again lead top class development in the next years. Just here is a picture of the group that we took a few years ago, and most of them are here. So, but just as a summary of this part, I still have the main goal to have access to state-of-the-art, high spatial, spectral, polarimetric observations of the sun. And in this case, it's just trying to help to get tools to continue doing that in the future. So, and again, because the important thing for me is trying to understand the sun. And just as a brief mention, when I studied my PhD, was mainly analyzing, the data and sunrise data. And recently, I continue trying at least to keep analyzing solar observations, but now I'm focusing more on high energetic events. These are the so-called flares that they are release of huge amounts of energy. And actually, some of the images that I showed you before, the inversion results and some of the context image, are actually one of the works that I hope to submit in a few weeks. And in this case, what we have is a flare. Here we have different context images. So this is from the full disk satellite. So this is not the ones that we are actually using for the publication. And we have continuum and information of the magnetic field. And then here we have information from higher layers in the atmosphere. This is the corona. And we have here that there's some activity. And here is much clearer that there's a really, really, really high activity that if we check the flags, we see that there's a peak, that a flare was happening at that time. And the good thing is that the observation that we are going to use that corresponds to the region enclosing this white square here was happening in between these two black lines. So it was just 10 minutes, and it was exactly at the peak of the flare that we are going to analyze. And then the regions that we are analyzing in detail is this one, but this is actually the field of view. As I said before, we are microscope-like, so we don't see the sun, we just see a small part with high spatial resolution. And then the inversions that I showed you before are inside, are the region inside this square. Okay, so still, I always try to have some time to continue analyzing the sun, besides doing also instrumental development and theoretical studies. So, as a summary, my goals have been and are to understand the various solar phenomena through the analysis, again, of spectropolarimetry and using inversion codes, but at the same time also to develop new instrumentation to help us perform better observations of the sun. And that's all. Thank you.
Thank you very much, Carlos. Now we have questions. We have a list of questions here.
Curiosity that at the beginning you showed several slides with a set of spots that for somebody from out of the field it looked like a weird shape, right? It's not like your typical group of spots. What's going on here? Why they are distorted this way? There is these correlations.
Yeah, this is not the normal one. As you said, usually we expect like some rounded shape. And this one is, I think, is distorted because just before this map, it was an X-class flare. That's one of the most energetic events. And I think this strange structure, some kind of light bridge that you have in the middle, it was slightly straighter before, and then after the flare, it goes really complex. But I would say that this is because it's a complex active region that actually, I think, produce like 3 X-class flares that are the highest energetic flares that we get. So why this one is so complex, I don't know. I know that because it's so complex, it produces a lot of energetic events, but actually there's a lot of activity there, and it has been one of the most studied sunspots in the last 10 years because it really produced like 3 X-class flares. Yeah.
Okay, any other questions? Comment?
Mobile. Concerning the spectral synthesis that you have done in 3D models, you have made a spectral synthesis for chromospheric lines, and what kind of approximations have you used for this spectral synthesis?
Yeah, so they were basically calcium 2 infrared, potassium D1. So the approximations were complete redistribution and 1D. Yes, yes. And I think, yes, this is the main thing. And in the case of calcium, definitely in general, we can get more or less accuracy with CAD. And in the case of potassium, we tested, we compare PAD versus CAD, and also CAD seems to be reasonable for the simulations that we have and the line of sight. So we were always at heliocentric angle 1. And then all the studies were either RH, well, essentially RH, with a complete distribution and CAD. Sorry, and what was it? CAD and heliocentric angle equal 1. So we didn't project any different angles. Is this your question? Yes. I don't know. I don't know. We can try to use Porta and compare, or maybe there's already publications.
Okay, more questions? Students have to ask questions. You're not a student. Well,
I'm a student. I am always trying to learn something. You said you are going to develop instrumentation. Which instrumentation are you planning to develop?
Is what I presented in the last slide. So actually right now, what we have been working more is Ember. That is an integral field unit based spectropolarimeter. Sorry, it's going to take some time. And it's going to be for the EST telescope. The main spectral range will be from 1 micron and above. So main target lines will be 1030, 1.5 micron, and additional spectral lines that we can have there. It's going to be integral field unit. So we will have the 3D information at the same time. So 2D and spectral and polarimetry. Ember.
Oh.
Yes. Why do you ask? Well, I thought, but at the end, this is a future development. So we have completed conceptual design phase. So now we are going to start preliminary design phase. This will take some years, and then eventually we will enter in final construction phase. So
the questions? I have a question because you have been working a lot on the inversion codes, right? And in this group, many people are also working in different inversion codes. So this field is developing in many different directions, like applying non-LT, applying physics-informed neural networks, 3D. What do you think will be the major breakthrough in this field in the coming years?
it's a difficult question. I think we always think about 3D as a possibility, but I think it's really CPU consuming. But I guess if we can really implement 3D somehow with reasonable times, I think this may help with a specific spectral lines. And I think also probably if we can really get a grasp of how to model spectral lines that we have been observing before, but still we are not able to really fit them properly, like for example, H-alpha Balmer lines. We have a lot of observations from these lines, but still doing proper inversions of these lines, we are not capable. So I guess combining 3D and improving models, atomic models for certain spectral transitions, spectral lines, I think this will probably help us to get more from what we have nowadays. And I think this combined with the future multi-channel observations with instruments, for example, from EST or the KIST, that they will cover various spectral ranges at the same time. This will probably give us access to a better high resolution when we perform the inversions, because one spectral line is usually limited. If we start increasing them, and spectral lines from photosphere, chromosphere, upper photosphere, I think this will probably help us constrain better atmospheric parameters.
Okay, more questions? If
You mentioned the EST, right? What are the major, what breakthroughs can we expect from this facility?
I think there are many. The first is we start from size. We are going to step up of a normal telescope of 1.5 meters to 4 meters. So this is a huge step. But one of the things that we can do when we take a huge step like that is to either go at and use diffraction limit such size, or we can try to stay in reasonable sizes like 1-2 meters, but then gain much more photon, so signal to noise. And as I said in the one of the slides, In some cases, we still have no polarization signals above the noise. So then we can try to use the extra size of EST to get better signals. And this combined with EST design. So EST design has been always focused on minimizing the number of optical surfaces and also arranging these optical surfaces to try to minimize the instrumental polarization. So then it means that for similar integration times that we have nowadays with current telescopes, we should be able to get much more signal and less instrumental polarization. So then it means that we are going to be able to see much deeper in the sense of polarization information. And this combined with a new generation of instruments that in principle, they will try to work at the same time coordinated. So then it means that we are not observing one spectral range. Probably we are going to observe several spectral ranges at the same time, visible, infrared, ultraviolet. And then also most of the instruments will be able to be integral field units. So then it means that we are getting better polarization signals, but we are also observing the sun in a different way. So we are not always just doing a scan or doing an imaging and then try to record different spectral wavelengths. We are going to have the 3D information at the same time, plus the increase in polarization accuracy. So I guess the main thing will be that we are going to get access to much weaker polarization signals than before at a reasonable spatial resolution, even better than the one we have nowadays.
So I think if there are no more questions, then we can send Carlos again. And now apparently we have coffee after seminar, so you can go there and have coffee.
Students that want their attendance to be registered, please come down, okay? Just the students. Thank you.